Right, so welcome back to part 4 in the 80th edition training. Now, we're now going to start breaking it down. So we're not going to do part 4 in one video because it's quite a lot of content. So what we're going to do is we're going to do chapter 41 in this video, and that's going to be covering protection against electric shock. Up to now we've done part 1, part 2 and part 3. And what we said in part 1 is, with the layout of the book, we said that the part 3, assessment general characteristics, is where we look at the requirements at the initial design point with regards to the supply characteristics, the need for maintainability, the need to verify compatibility, the need to consider division of installation, obviously knowing the client's purpose, and also the maximum demand and all of those things. Having obtained that information, we would then have to comply with the fundamental principles which we mentioned in part 1. And those fundamental principles said that we must protect persons, livestock and property from the risks that using electricity can create, and that was shocks and burns and all this other stuff. So whenever we design a system, we have to identify the needs of the client with the assessment of general characteristics. What we then have to do is choose methods of protection. Now, we also said in part 1 that we have basic protection and fault protection, and we said that basic protection was protection against electric shock in a fault-free condition. So there are no faults, there's no issues with the system. What stops you being able to receive an electric shock in normal use? And we said the common solutions there would be insulation, barriers, placing out of reach, and a couple of specialised scenarios might be isolating transformers. We then said we also needed fault protection. We said that fault protection is protection against electric shock under a single one fault condition. And the common example of those was earthing and bonding and the suitable protective devices. We also could use a supplementary layer of insulation or an isolating transformer for that. So we did say this, and we said that basic and fault, 2 scenarios, one's fault-free, one's single fault. Now, we have what's recognised as protective measures, and protective measures, or general protective measures, have to have a combination of these two, basic and fault protections. And that's going to be the main focal point of this video. It's chapter 41, protection against electric shock. So, starting at the beginning of that, we have 410, section 410. It tells us, there we go, it deals with the protection against electric shock as applied to electrical installations, and it's based this on BSEN 61140. Now, BSEN 61140 is another British standard, which, as you can see here, protection against electric shock, common aspects for installation and equipment. So it tells you about the requirements to protect against electric shock. It basically goes along the line of, and it says here, the fundamental rule of protection against electric shock, according to this standard, is that hazardous live parts will not be accessible, and accessible parts will not become hazardous live. And it's a very obvious principle, and that is given in this standard, and it's taken out of this in manufacturing standards, in plant standards, in equipment standards, and obviously in our wiring standards as well here. But that's an obvious fundamental thing, but that's what we need to verify, and that's where this comes from. So, scope we have there. This chapter specifies the essential requirements regarding protection against electric shock. Includes basic protection and fault protection of persons and livestock. It deals with the application and coordination of these requirements in relation to external influence. So, deciding on the ways to apply basic and fault protection. General requirements. In the standard, the following specifications of voltage is intended unless otherwise stated: AC, RMS, and DC. Right, so here's the first mention of these protective measures. So, reminding ourselves now of basic protection and fault protection. So, basic protection there, we have live parts in an enclosure. So, inaccessible. Can't touch them. Fault protection, live parts. Fault condition, exposed parts become live under a fault. If it's a class 1 or a metal encased appliance, it can become, so it's an exposed conductive part. It can become live under that fault condition. We then have protective earthing and bonding to take that fault away. If it was obviously class 2 construction, it would be insulated, then we still would not receive a shock because it's not an exposed conductive part. So this is basic protection, this is fault protection. It's very important that you just try to keep repeating that in your mind as we go through the rest of this chapter, because again, common exam questions could say, which of the following achieves basic protection, or which of the following is a method of fault protection? And so you've always got to understand what basic is and what fault is, and when we get towards later into this chapter, it'll make more sense how they could use that in your exam scenario. So, 410.3.2. Protective measure will consist of an appropriate combination of the provisions of basic and independent provision of fault, or enhanced protection provision which provides both in the same scenario. So we must have basic protection and we must have fault protection at all times within our electrical system for it to comply with protection against electric shock. Now there are specialist scenarios, which we'll mention towards the end, but when we say a protective measure, we need to say, well, okay, some protective measures are good for specialised locations, such as placing out of reach or non-conducting locations, but then we need to say, well, there must be a specific protective measure that is, more applicable on the wider range, so we can install it in the home, we can install it in the workplace, and not need to make sure that those places are guaranteed occupancy by electricians and people monitoring the use of those systems. And that's what we call general protective measure, and those are given in 410.3.3. So it says, in each part of an installation, one or more protective measures will be applied, taking into account the conditions of external influence. The following protective measures generally are permitted. And these are the ones we're going to focus mainly on in this video. So we have automatic disconnection of supply, known as ADS, double or reinforced insulation, electrical separation, and it's important to know that this is for one item of current using equipment only, and then extra low voltage via the provisions of SELV and PELV. These are classed as general protective measures, and they are accepted in the ordinary person environment. Okay. So throughout this, as we go through, we're going to remind ourselves of how, with this is ADS we're talking about now, so this is automatic disconnection of supply. Okay, 411. If you go down to 411, we're discussing the very first protective measure. So in this protective measure, we achieve basic protection by simply installing cables that are always sheathed, and when they're no longer sheathed, so we've removed the outer sheath, they are in an enclosure. So whenever you're doing an EICR and you see a cable, and you're not in an enclosure, you're not in a controlled area, you're just wherever, and the sheathing has been stripped back beyond the accessory, and you maybe have a little bit of brown or blue visible, you've got to start saying to yourself in your mind, well, that is actually now failing to achieve compliance with the protective measure of ADS. And it, sounds a bit, obvious, but it's important that you remember things like this. Same as barriers, obstacles, and enclosures. If we have lids missing, or if we have doors that won't lock, we've always got to say, well, what is that achieving from an electrical perspective? Okay, so basic protection is often achieved with those. Now, with regards to fault protection, we most often would utilize a bonding scenario and a earthing scenario for our final circuits, and we have to combine those, because if you remember what we said way back in the first video, we said that earthing is there to limit the duration of these faults, the duration of the earth faults. The bonding is to limit the value of potential of those faults. So I have to have both. If I don't have earthing, I'll just have a low value of voltage in a fault condition, but for a very, very long time. If I just have earthing, then I can have this very, very, very quick fault scenario, but could be at a magnitude that's really high and is rather dangerous. So we have to have those working together. And that will only work, though, if there is a device protecting the circuit that will identify the large currents and will actually operate that. And that's the whole principle of ADS, isn't it? So we probably are very familiar with this. We chase after this with testing courses and with other areas where we do things like this. The good old Earth fault loop return path here. So you have your supply transformer. This could be, it could be on site. If you're on a large site with its own, dedicated supply, it could be that it's down the road behind a gate or in a little fenced-off area where all the footballs and frisbees end up getting lost. But this is your supply transformer where the distributor takes their high voltage from the network grid. They will then step that down to low voltage, and then as a ring main, it'll be distributed, and then you'll pick up on that. That's quite often how it'll happen in the rural areas. So then there's this distribution cabling, which will come to your intake position. So this is the supplies cable, and then you have your intake position here. So this is your main service head, your main intake, your main switch room, and then you have your final circuitry to your final point of utilization, and you have your exposed conductive parts. And we know these terms. We're not doing a testing course, so I'm kind of going through these fast. But we have our supply loop, known as the ZE. We have our internal loop, known as the R1, R2, and then we have the overall loop, known as the ZS. That formula, I haven't actually got it written down here, but the formula, ZS is equal to ZE plus R1 plus R2. It's not written in the document, but that could be a question, because they always throw that kind of thing in there just to kind of see if you understand the principles of ADS. And it's a common way to illustrate the principles of ADS, having to ensure that we have an overall loop of impedance that will actually achieve a significantly high fault current. So, do make sure you're familiar with that and the purpose of this whole scenario. Okay, we'll come back to this, and I'll talk us through this as we push through section 411. So, with regards to basic fault protection, it just says, this is back to general 411.1. It says basic protection is provided, barriers enclosed in accordance with, and it tells you to go to 416, or it says to consider the other regulations. Now 416, if you actually turn to it, that just tells us typically about the insulation being to IP2X or IP4X horizontal top surface, IPXB, IPXD, insulating properties. Really, that's all that gives us, and that's all we really need. And then it then says full protection by protective earthing, bonding, and automatic disconnection in case of a fault in accordance with 411.3 to 411.6, and that's really where a lot of the content of this section will come from, in the fault protection part. So, a requirement for basic protection: all equipment shall comply with one of the provisions for basic protection described in section 416, or where appropriate, 417. For fault protection, protective earthing and protective equipotential bonding. So, for earthing, the exposed conductive parts will connect the protective conductor under the specific conditions for each type of system earth, as specified in 411.4 to 6, which we'll come to. Now, they represent TN systems, TT systems, and IT systems. Simultaneously accessible exposed conductive parts will be connected to the same earthing system individually, in groups, or collectively. Conductors protective earthing will comply with Chapter 54. Chapter 54, which we'll come to obviously later on, that's the sizing of the earthing conductors. Circuit protective conductor will be run to and terminated at each point in the wiring and each accessory except a lamp holder that has no exposed conductive part and suspended from such a point. So, you know, your typical ceiling rays. With regards to the earthing, then, this just further illustrates the ADS and how this slide just illustrates how ADS works and how the impedance will result in the voltage presence on different cables. So in an earth fault loop, there's the higher voltage across the earth, and that's the intention here of ADS. But we'll actually summarize this as we get through. Earthing and bonding. So the earthing, we establish the supply earth arrangement, main earthing terminal, and we go off to the final circuits. Now this is a simple illustration. You could say this is a TNCS, I guess, considering I guess that's a bit rubbish, but that's what that's supposed to look like. Do remember that we said in definitions part 2 video about that poor illustration at the back of the definitions and how it illustrates the main protective bonding conductors, the circuit protective conductors, and the supplementary protective bonding conductors, and the main the main terminals and stuff. And if you're unfamiliar, illustrations like this are a little bit more helpful, but they may not use them. Earthing itself, then, we just kind of said that we need to identify every single exposed conductive part in an electrical system. This is just a typical kitchen, and just shows you which parts we need to verify. Now I'll be saying a lot now, but I'll also be saying a lot more when we talk about bonding, that when we do verify the need for supplementary bonding, what we'll try to do is take a value of resistance measurement between accessible exposed conductive parts. So the question of whether or not we need to have supplementary bonding, which we'll come to very soon, will be dictated by the value of resistance, maybe from this. Say that this is on a cooker circuit, and let's say that there was a pipe or something that was connecting to this piece of equipment, and that there was a touch voltage between the two. Only if they're within arm's reach of each other for the normal user or the normal occupier of the installation would we need to consider the need to have supplementary bonding. But obviously with things like RCDs, that's becoming a lot more unlikely. And again, we'll touch on this a little bit early, but we'll be getting to earthing and bonding, or more importantly, bonding and the voltages as we push through. But this just illustrates how much of the actual location requires protective earthing. All these class 1 items of equipment will become exposed conductive parts of the electrical system, and so ZSs are very essential to make sure that these things will disconnect in the required time frame. Equipotential bonding, then, 411.3.1.2. In each installation, main protective bonding conductors complying with Chapter 54, again, sizing of the bonding conductors, shall connect the main earthing terminal, extraneous conductive parts, including the following. So water installation pipes, we have gas installation pipes, other installation pipes, for example oil, central heating, air conditioning, exposed metallic structural parts of the building, RSJs or whatever. It then says metal pipes entering the building having an insulating section at their point of entry need not be connected to the protective equipotential bonding. This is actually new in the 18th edition, but this has been around for years now. It was in the on-site guide recently, but a lot of electricians still kind of get confused over it because they assume that if it comes in, it can pick up a reference point of earth. It may internally pick up a reference point of earth from a CPC, but that again is common to the main earthing terminal, and so isn't a need for main bonding. Now there was a mention of bonding the branch pipe work, which can obviously confuse some people. This is the regulation here. So, this is a picture that I took in the kitchen. This was just under the kitchen counter. The water came up as a insulated pipe. Then it was copper pipe thereon. I could easily have done a measurement. There is in Guidance Notes 3, there is a value of resistance. It's it's a high kilo ohm value, 22 odd kilo ohm, but it gives you the understanding of whether or not this would be warranted as an extraneous conductive part. But fundamentally, it didn't need bonding. But and I'm going to go into it very briefly. The requirements of the bond, which we'll see in chapter 54, is at the point of entry to the building. So obviously this will come in, there'll be a stopcock. This will come in, there'll be a stopcock, and then obviously we would normally bond there, but not in this case because it's insulated. If this went obviously into the building, then it could become an extraneous conductive part again if it was to go back underground. Now I saw an example like this at a kitchen that I was working on in High Wycombe, where the client had a gas hob and a sink on the island in the kitchen, so the service pipes were actually buried in the concrete in the ground, and at that point I had to reapproach them as extraneous conductive parts again, because they weren't insulated, they weren't plastic, it was just copper pipe work. Actually, can go down into the ground, and at that point they can pick up a reference of earth. So it's frustrating that in the regulations we say bond that pipe as it enters the property. What they're trying to do is oversimplify this. They're trying to say that pipe coming in, bond it if it's metal, and if it's not metal, don't bond it. What we need to recognise is if anything brings a 0 volt reference to the property, so anything comes from underneath the ground or the foundations that is conductive, that comes in to the equipotential zone that we have created, that is also conductive. If it comes in our equipotential zone, it's providing a stake or a rod of a separate potential. We have to bond that so the extraneous conductive part coming in joins within our equipotential zone. So anytime we have a gas pipe, a water pipe, an RSJ, or internally within the building a pipe re-enter the ground and then resurface, it still needs to be checked that it's a new reference of 0 entering our equipotential zone, and we bond the crap out of it. That's when we choose to bond it. What we don't do is say, oh, it's at the point of entry, it must need bonding, because we can do excessive bonding. We mustn't do excessive bonding. We need to make sure we understand what we're bonding for. Purpose of bonding is obviously with regards to lowering the potential voltages that can occur, so we need to understand touch voltage. There's no real mention on this, or no real obvious identifying what touch voltage is in the standard, but what they do, and we'll see this a bit later on, is whenever there are concerns about the presence of a voltage on exposed conductive parts, or we're relying on RCDs to be a method of disconnection of the supply, we always use a voltage of 50 volts as our limit of voltage. We always say that in the presence of this circuit, we'll install a resistance that will, with regards to the IA of the protected device, result in a voltage in the fault scenario that does not reach 50 volts plus. That basically means touch voltage. So we don't say it in the regs, but we use it in the regs. So the whole purpose of the bonding is to ensure that between exposed and extraneous conductive parts, the voltage in a fault scenario stays lower than 50 volts. Similarly with extraneous to extraneous conductive parts, the voltage in this scenario must be less than 50 volts, and we'll figure all that out with bonding later on. Moving back to the whole earthing thing now, so we'll go to 411.3.2. So it says, except as provided by 411.3.2.5, which says if it's not feasible, which on a new installation, it should always be feasible. But if you're working on the existing, I can understand that. A protected device will automatically interrupt the supply to the line conductor or the circuit or equipment in the event of a fault of negligible impedance. Negligible impedance just means low resistance. Between the line conductor and the exposed conductive part or the protective conductor in the circuit or equipment within the disconnected time required by 411.3.2.2, 411.3.2.3, and 411.3.2.4. The protected device shall be suitable for isolation of at least the line conductor, so it must be able to operate as a disconnecting device for the line. Okay, and isolation might just look like an easy word there. We're going to see later on in chapter 53 that, isolation is a method of switching, and we need to recognise that the isolating device is recognised in BS 7671 as an isolating device. Right. So this is where it gets a little interesting. So, 411.3.2.2, the maximum disconnection time stated in table 41.1, which is illustrated here, shall be applied, and it's very important you understand these little words that mean a lot. applied to final circuits with a rated current not exceeding 63 amp with one or more socket outlets, and 32 amps applying only fixed connected current using equipment. Final circuits means a circuit that then reaches a final point of utilization. So this is not a distribution circuit. So if I'm going to install a circuit from the house going down to the shed where there's another fuse board in there, that's not this. If it's a circuit, let's say within the shed, going to lights or to sockets, or in the house or so that's going to the shower or the cooker, these are final circuits. So a final circuit for 63 amp for one or more socket outlets, that's actually increased. That's increased from what it used to be. So obviously we can have socket outlets, plug and socket outlets, 32 amp and 63 amp. So they've now gone up to the 63 amp one. I can understand why. It's a regular point of utilization. I see that a lot in the food industry where I do work. But it's a socket outlet circuit. So a 63 amp socket outlet, single phase or three phase. The three phase are the big red C form ones, and you're going to plug that large plug into that socket outlet. That will require the quicker disconnection. But if you actually didn't want that, you could always just change it to a rotary isolator method. You'll have to change the method of utilization there. And for any other circuit, 32 amps supplying one fixed connected piece of current using equipment. So if I had a shower that was 32 amps, I'll be looking at table 41.1. If it was a 40 amp, it would actually be not within this regulation, and it would be within Form 1.3.2.3 or 4. So let's assume that I'm using a 32 amp socket outlet circuit or a cooker at 32 amp, and so I have a socket outlet circuit up to 63 or a final piece of equipment up to 32. I need this table. The question then is, what's my earthing system? If my earthing system is a TN system, then I am 0.4 seconds. If my earthing system is a TT system, 0.2 seconds. We're sticking with AC for this. Alright? So that seemed fairly easy, but we are going to repeat that a lot later on when we start looking at cable selection, because we'll say, okay, we have this cable type, and how many amps is required to disconnect it. That will always be determined by this part, which tells us the maximum required disconnection time. So I'll give a scenario later on, maybe in part 5 or later on in part 4, where we talk about a protected device type and the required current to disconnect it, for ADS, and we'll have to find out what that time is. So we'll start here. It always will start here. What's the earthing system? TNCS or TNS? It's a TN system. TT system? Okay. Is it a final circuit or a distribution circuit? If it's a final circuit, then okay. But does that final circuit go over 32 amp, or is it socket out over 63? No? Okay, you stay here. If you are a distribution circuit, or you're a final circuit over 32, or a socket outlet of 125, or if you are that high, you move on. And you move on to Form 3.2.3 or Form 1.3.2.4. Those two regulations, you'll see, say, okay, so the table's not applicable. So for a TN system, 5 seconds. For a TT system, 1 second. Okay, so we're going to repeat that a lot later on. But those are the maximum required disconnection times for general protective measure of ADS. We will see later on that other systems like self systems or reduced low voltage systems will have 5 seconds as the maximum disconnection time due to the different characteristics of the way they protect against electric shock. But for general protective measures, we're looking here at these disconnection times. Okay, moving on through a bit. Form 1.3.3, additional requirements. This used to be called additional protection, really, but it's additional requirements for socket outlets and for the supply of mobile equipment for use outdoors. This has also had a minor change in the 80th edition. So it says, in an AC system, Additional protection by means of an RCD with a rated residual operating current not exceeding 30 milliamp. That's why we see them everywhere. Will provide for socket outlets not exceeding 32 amp and mobile equipment with a rated current not exceeding 32 amp for use outdoors. Now that 32 amp used to be 20. They've pushed that up to 32. This is the same. They've changed the exceptions. It now says an exception to one above the socket outlets here is permitted where, other than for an installation in a dwelling, there is a documented risk assessment determining that this RCD protection is not necessary. They tried to, in the public draft of the 18th edition, they actually tried to actually not have this, and it was just RCDs everywhere. But there was enough comment on the draft, and they reintroduced the risk assessment approach. But the risk assessment approach is not accepted in dwelling environments. It's just not accepted, which I guess makes sense, because the risk assessment for a dwelling is not really, from an electrical perspective, easy to control. The labeling of the socket for a dedicated use, that's been removed. That's not there anymore. So now the only reason or method to not have an RCD is a documented risk assessment. And one of the areas that I see quite a lot not executed very well, these risk assessments. So do think about that. We have a new regulation here, Form 1.3.4. This tells us that if we're having any circuit in which a luminaire will be supplied, I mean, you could just say that's light circuits, but I guess if any circuit was supplying a luminaire, that would come under that then. But they're basically saying in the domestic or the dwelling world, circuits that supply luminaires need to be on a 30 milliamp RCD. There could be a number of reasons why they've introduced this. I can expect, though, quite often that it's probably due to the fact that a lot of us will go to the shops and buy these things and then connect them, and there are risks of fire for properties where when the generic homeowner can go down to the local shed, the local B&Q, buy a luminaire, and have a go at putting it up themselves. There's nothing against building regulations with that, and in their bedroom or whatever. And you can just see that loose connections, risk of fire. RCD is a method of protection against fire. So electric shock risk. So I can see why they've done that. I can see why they've considered that necessary. Okay, so we're now going to carry on talking about this ADS, disconnection supply. We're going to refer it specifically to TN systems now, and this is important because a TN system has a combination with neutral and earth and a distributed protective conductor, either separate or combined with the earth. So when we actually have an earth fault, the earth fault loop return path will then utilize this distributed protective conductor, and that results in a path of negligible impedance, again, little resistance. When we have a path of little resistance, we get high, significantly high fault current, and that's actually our objective. Our objective is to create a circuit, supply it with a low impedance path so that the fault current is high. High fault current equals quick disconnection, and we've just discussed disconnections. We just discussed that the disconnection time for the TN system was 0.4 seconds for a final circuit and 5 seconds for a distribution circuit. So it's important to make sure we have a circuit and a current that's there that's going to achieve this rapid disconnection. So with TN systems, we're making sure that this is going to work, and that's what we're going to do next. So the characteristics of this circuit will work. With TN systems, it tells us the circuit's impedance shall fulfill the following. The ZS times the IA must be less than or equal to UO times Cmin. So ZS is the impedance in ohms of the fault loop comprising the source, the line conductor, and the protective conductor. So the Z, this is where there should be a formula here. The ZS is the impedance of the source, ZE, the line, R1, and the protective conductor, R2. That's where that formula should really be written. IA is the amount of current that causes automatic operation of the required disconnecting device. So we would typically say, okay, how much current is required to achieve disconnection? We'll go with that current. UO is the nominal voltage that's present in the fault, and then there's Cmin, which is the a factor taken into account the voltage variations, which we had introduced in Amendment 3, which is 0.95. So that's all there in the regulations. It then says the following types of protective device may be used for fault protection. Let's remind ourselves we're talking here about fault protection. We can have an overcurrent protective device or an RCD. When RCD is used for fault protection, the circuit shall incorporate an overcurrent protective device in accordance with Chapter 43. So there'll still be need for overcurrent protection with regards to this ADS. And if you think about it, an RCD is not going to disconnect a short circuit, is it? Because an RCD works on imbalance and leakage current to earth. So we need to have an overcurrent protected device for short circuit scenario. Maybe even an overload if overload protection is needed. Okay, so let's just get on looking at this table then. We have this table here. Well, that's actually just 41.3, which is the middle table. Let's look at that middle table, 41.3 first then. So this table gives us maximum full loop impedance ZS for the circuit breakers of 60898s and RCBOs of 61009s. And it gives us type Bs, type Cs and type Ds. And it gives us the rating of the breakers, and it gives us the required full loop impedances. The way that these values are obtained is by understanding how much current is required to achieve this disconnection time and doing Ohm's law with it. So if we went to Appendix 3, which is where the book goes a bit funny looking, in Appendix 3 we call these the time curve characteristics, and we'll find one of these will be titled Figure 3A4. Type B circuit breakers to be SCN 60898 and RCBOs to be SCN 61009-1. The next page is the type C, and the next page is the type D. Okay. So when I look at this curve, it tells me, I can look at it in two ways. I can either look at the table or I can actually look at the curves. But it tells me all the different protected devices. So there's a 6 amp device on there, a 10 amp, a 16, a 20, a 25, a 32, a 40, a 50, 63, 80, 100 and 125. All along the top of that curve line. I look down the left of this chart and it shows me time in seconds. So going from the very bottom as I go up in 0.1 intervals. 0.01 intervals. Then I go up in 0.1 intervals, then in 1 intervals, and 10 and 100 and so on. I go along the bottom, I have current climbing in 1s to 10, then 10s to 100, and 100 to 1000, etc. If I wanted to figure out how much current is required to achieve 5-second disconnection, I'll just go up on the left to where I get to 5. So I go to 1, then I go 2, 3, 4, 5 to the line. So in between 1 and 10 really. So 1, 2, 3, 4, 5. And then go all the way along until I find the vertical line representing the device I'm looking at. So if I go to the 6, it then goes 1, 2, 3, 4, 5. It shoots down, and then I notice that's a vertical line. I go across the current at the bottom, 10, 20, 30. That tells me that 6 actually trips in 30 amp, but I could have just looked in the table because it tells me that there. Okay. So being able to read these charts is pretty important, but they are fairly summarized, and a lot of the questions in this area will be summarized anyway. But let's take a look at that. Let's go to the scenario. Well, this just shows you this. Let's go to this one. So we have a 3036 table. So if I go to the 3036 one, which is back on page. Well, there's two. There's one on page 366 and there's one on page 365. I'm looking at the one on page 365 because that's the one that has the 30 amp fuse in it. So if I look at the semi-enclosed fuses to BS3036 chart on page 365, I can see there's a 30 amp fuse on that. Now if I wanted to figure out the fuse requirement for 0.4 second disconnection, the table actually tells me 30 amp, 0.4 disconnection, 210. So I need 210 amps to disconnect a 30 amp fuse in 0.4 seconds. Now if I needed it to be 5 seconds instead, because it's a distribution circuit and not a final circuit, I only need 87 amps because it needs less current because it's a longer time. More current, quicker time. That makes a lot of sense. So understanding the required disconnection times is quite important. Alright, so the BSCN 60898 we just looked at though, they didn't have times because they actually achieve the same level of current will achieve disconnection in 0.1 to 5 seconds. I don't know if you noticed that, but the same level of current due to the combined ways that the MCB works with bimetallic strip and the actual electromagnetic field through the pot works very clever, but the same amount of current will achieve disconnection within 0.1 to 5 seconds. So there's only one value of current required. When we come to fuses though, like this 3036, there are varying amounts of current required to achieve varying disconnection times. So I need to calculate a current for 0.4 seconds. I need to calculate a resistance for 0.4 seconds, but I also need to calculate a resistance for 5 seconds, and I have to put them both into a table back in part 4. Well, they've done that. So if I go back to part 4, to where those tables were, in chapter 41, one of them is table 41.2, and the other one is table 41.4. When I look at table 41.2, and table 41.4, I'll actually, if I keep flicking between them, they both have the same fuses in them. They're both BS88 88.2s, they're both BS88.3s, and they're both 3036s. But I'll notice that the actual fuses in one of them only goes up to 63, whilst the other one goes all the way up to over 100. And then I'll realise when I look at the actual titles of these tables, that one of these tables is for a 0.4 second disconnection time. Remember, this is a TN section. So 0.4 second disconnection time for table 41.2. And table 41.4 is the 5 second disconnection. And as we just said here, different levels of current are needed to achieve disconnection times that are different. Therefore, different impedances are required to achieve those different current levels. So the earth loop impedance is different for 0.4 seconds or 5 seconds. So we have two tables for that. Now it's important that you can understand that, because we'll use this a few times as we push through. But you can have in your exam a typical question would say the required value of earth loop impedance to achieve automatic disconnection of a final circuit not exceeding 32 amps, so you go 0.4, or of a distribution circuit you go 5, and you have to decide which table. And some people do get caught out with that, because City and Guild, as a good example, would give you the answer from both tables. So if they said a 30 amp 3036, they would actually give you 1.04 and 2.51. Bastards. But they would, because you can easily take it from the wrong table. So it's important to understand that those tables achieve different disconnection times, and the reason we need different disconnection times is because we have to achieve the difference between a distribution circuit and a final circuit. And again, if we think about what we talked about yesterday, or in the previous video, we did talk about the need for division and selectivity and discrimination. So it's important that final circuits isolate before distribution circuits, because those distribution circuits could obviously go to other final circuits as well. So this is all part of selectivity to make sure that the protected device local to the point of fault disconnects first. Okay, so we're going to come back to look at this area when we look at sizing of protective conductors and sizing of live conductors. We're going to use this data and we will repeat on it, but I'm not going to carry on doing examples on how to determine earth for loop impedances at this point, because we need to push on through the rest of this chapter and the rest of this video. But if you do want more info on it, then just hit me up and I'll provide some more content and some more information on this section. Not a problem. Okay, so that talks about the TN, and then, as I said earlier at the beginning of this video, TN uses the supply protective conductor. It's a very low impedance because it's a big copper or a big lead sheath or a big steel cable, whatever. So it's a low impedance. We can use it to achieve high fault currents. Unlike the TT system, where we have the mass of Earth and we do not have this low impedance pathway for our Earth loop return path. This is why TT systems is separately covered. We can't use the Earth for loop impedances for the final circuits for TT systems because we just won't achieve this low impedance. If we can, we can. It does allow that. It does say with TT systems at 411.5.2, it does say we can use an overcurrent protected device, but for you to use an overcurrent protected device, you have to achieve that current. So, if you can, you can. If you can't, just you're stuffed. You've got to use an RCD. And the reason we have to consider using RCD is because the RCD doesn't actually work on an excessive value of fault current. It works on obviously monitoring the currents it needs to and determining there to be an imbalance. So they're a lot more sensitive and they're a lot more practicable for TT systems to identify a leakage or a fault to Earth. So that's why we use them, and we install them obviously at the origin because that's the point of isolation now. But you'll notice, unlike the TN systems where we said, okay, well that voltage is going down that protective conductor through that circuit, we are going to verify that using a 230 volts voltage in this Earth for loop impedance. Here under Form 1.5.3 it actually says, jumping ahead now, so here it actually says, it's just an illustration of the electrode for a TT system, that if it's used for full protection, the following conditions will be fulfilled. The disconnection time shall be that required by Form 1.3.2.2 or 3.2.4. So the TT system for a final circuit up to 32 amp, we said was, think about that, yeah, 0.2 seconds, yeah. Final circuit was 1. Sorry, distribution circuit was 1. So we have quicker disconnection times required there. So we have to achieve those, and also it says the RA times I delta N must be less than or equal to 50 volts. Now the RA, it says, is the sum of the resistance of the earth electrode and the protective conductor connecting it to the exposed conductive parts in ohms. So it's resistance of the main earthing terminal point of the electrode to the exposed conductive parts within the system. I delta N is the rated operating current of the RCD, but we're talking about an earth imbalance, so we're saying milliamps, 100 milliamps, 300 milliamps, 500 milliamps, 30 milliamps, whatever that is. Okay, there's nothing that says it has to be 30 milliamps. It has to be appropriate, but it does say the voltage there must be no more than 50 volts. It must be less than or equal to 50 volts. All right, so when we actually install an electrode, we know that we have a guidance there. It gives you in note 2 of table 41.5, and it does say, a value exceeding 200 ohms may not be considered as stable. But when we take a value of earth electrode resistance, we have a value of RA. What we then need to verify is the amount of current required to disconnect the RC in an imbalance. So that's just the milliamps. So we take the maximum earth for loop impedance in ohms, ZS, as given in this table, yeah, is dictated by 50 volts over the RCD. Okay, and that's why you'll see a lot of people with 30 milliamp RCDs and domestics will now put 1667 on them, because 50 volts over 0.03 is 1667. When we do a design, we're supposed to consider selectivity. We want to have an RC that's going to actually, work but not disconnect all the time. So it's better practice to try to actually install a larger RC like a 100 or a 300, but we need to verify the RA first. So if you have an RA and your RA is somewhere around the realm of 500 ohms, then you know that you can use a 100 milliamp RCD. So it's always, you could say it's selective. You need to verify that the electrode resistance or the RA is measured, verified it's good and effective, and you can then use that to determine what RC protection is required. Don't just throw a 30 milliamp in there. Wherever current protected device is used, the following conditions shall be fulfilled. ZS times IA must be less than or equal to UO times Cmin. So it uses the impedance again there. Okay, so that covers TN systems and TT systems. We then have 411.6, which I'm not going to go into too much detail on because they don't really touch it, but it's kind of a whole video content itself. But what we're talking here about is the IT system. It's a very, very, very good system. Okay, the IE is obviously it's like an isolation earthing system, and if you remind yourself of the earthing arrangements, the whole thing with an IT system is we have a distributed system, but the earth has a high impedance connected between it and the live conductors. So we don't have a neutral on this system, because neutral, is neutral because of its reference of an earth. There's a high impedance between that. So on IT systems, a bit like with reduced low voltage systems, there is no neutral. It's kind of like a live conductor and a live conductor with the potential difference between the two. So here we have the cables distributed, and you'll notice the equipment is connected between two of the lives there. Okay, so they're not neutral. They're all at the same potential differences between each other, and so you'll get maybe 230 volts between the two or whatever. But here's the magic of this system. The magic of the IT system is that when a single fault occurs, such as is illustrated here, to the exposed conductive part, the actual protective conductor will actually operate, but due to the high impedance, think about Ohm's law, the high impedance in that pathway will result in a very, very, very small trickle current, almost like a capacitive current maybe. So little that exposed conductive parts and things will not become at live potentials to the rest of the working area. It's isolated from the working area. The high impedance results in very, very low current. But the problem is, we've got it operational, but do we know about it? And quite often we won't. When these faults occur, currents flow to the protected conductors, but the very high impedance results in very low currents, so we don't notice it. So these systems require monitoring systems, insulation monitoring systems, or residual current monitoring systems to actually identify these changes in currents. And that would result in them needing an alarm system, which is fine, but it means that their use needs obviously someone to respond. And quite often they'll be used in a location like in a medical location, or maybe in a data center or somewhere. But they'll be used in a scenario where you'll have someone who is skilled or instructed to act if there's a scenario to isolate, to remove, or whatever. But where they are useful is we talked about basic and fault protection. The IT system, whilst with TN and TT, we've established fault protection to achieve disconnection, high impedances or RCD disconnection. The IT system will actually identify the fault condition. It will then allow the pathway to earth to flow at a very low level due to the high impedance, but the monitoring system will alarm people, but at the same time it will remain operational. And this is a very, very good thing for continuity of supply. So when you have sites that require continuity, IT systems are a very, very ideal solution. They just require that extra bit of management. They require that extra bit of nurturing and care, because you shouldn't obviously wire into it, parts of a separate system, because you can then completely void the protective measure. If you were to connect, for example, to the exposed conductive parts of an IT system that had that significantly high impedance, if you were to then connect them to a common earth part which has the low impedance, you're then voiding the protective measure altogether. So they do require a little bit of nurturing and a little bit of monitoring. They have alarm systems and things like that, but they're a very, very good system, and I can do a dedicated video on how they work and how they should be tested, if you want. But for completeness, that's really all we need to cover, is just an understanding of why they are used and where they are used and why we're going to see them later on in medical locations. And that's it. But that's all we'll cover with them for now. Okay, there's a bit of, again, because we use the earth, as a pathway, we do need to make sure the voltage there will not be more than 50 volts. The voltage can be up to 50 volts. It's the current that we limit through the high impedance. And that's what's good about this method of protection. It's a very, very safe system. Just requires a little bit of babysitting most of the time. We then have, after the IT system, we have FELV 411.7. We have SELV and PELV, which are their own protective measure in their own means, but obviously FELV is a functional extra low voltage, and so because the protective conductor goes across the transformer but works as a functional purpose and not a protective purpose, it has to be considered as a piece of equipment that works with ADS. It has to go onto ADS as a system, and it in itself cannot be considered as its own protective measure, because it doesn't really, in its own way, try to achieve protection. Okay. We then have further down 411.8, the reduced low voltage system. The reduced low voltage system we often see on construction sites and things like that, where you have your 110 transformers and stuff. The benefit of the reduced low voltage system is we have an isolating transformer here. Where's my mouse gone there? An isolating transformer here, and we have the winding. You'll notice that the earth comes across, it has the center tap, and it comes across and runs with the circuits. So obviously all the equipment can have a reference to earth, but it also has a link to the center of the secondary winding. And this is the magic really with a reduced low voltage system. We've mentioned before that 50 volts is considered the desired value of voltage in a fault scenario. Anything over 50 really can be considered as dangerous in electric shock. But the problem with having circuits like SELV or PELV in construction world is there's not enough power there to actually get work done. So obviously you may charge your battery at 18 volts, 24 volts, but when you actually go to do the work, that'll get you some way through joists and some way through a wall. When you want to drill like a 9 or 12 inch hole for a core cutter or something like that, you're going to want to go and get the actual mains powered equipment. And that's because we need the voltage and we need the power, and we need the power to do the work. So from a safety perspective, we still need this voltage to do work on site. So what we do is we use this transformer. And the way it works is quite simple. So you have a live conductor and a live conductor, and that's important to know. So when you have a reduced low voltage piece of equipment, the three cables are protective conductor and two live conductors. They're not live and neutral. Not both of them can go fault to earth. Okay, L1 to earth and L2 to earth, as you see here. They can both fault to earth, and they can both fault to earth at 55 volts. So if I had a fault between L2 and earth, a short, a damaged piece of equipment, what will happen is the current will flow from there, and it will then flow back, and you'll see it goes into half the winding. So as it's only going through half the winding, it's only half the voltage within this earth fault loop. So we have half the voltage in the fault scenario. To add a little bit to this, there is a lot of there's a lot of development needed in testing, because a lot of people don't know how to test these kind of systems, because technically with this kind of system, you want to do an earth for loop impedance external twice, because you have two of them, and a ZS within the system twice, L1 to earth and L2 to earth. And whilst they would technically be the same, you should be recording them and testing them suitably. Similarly, you should use a test instrument that works at that voltage. And also you want one that's a 2-lead one and not a 3-lead, because when you have a 3-lead to do a ZS test, you'd normally put the neutral on to 0 to combine that, but there is no neutral distributed here, so you shouldn't use a 3-lead tester, but that's kind of going a little bit extra here onto reduced low voltage systems. But what do we need to know in the regs? What does it tell us? Well, it tells us with reduced low voltage systems, it tells us that between 411.8.1.2, 3 phases, the value of the voltage shall not exceed 63.5 volts to earth. Single phase, 55 volts to earth. So that's the 55 volts given here. It tells us about basic protection being the 416.1, IPXXB, IPXXD respectively. It then tells us requirements of fault protection. It actually tells us that at the end of that paragraph, the earth for loop impedance at every point of the utilization, including socket outlets, shall be such the disconnection time does not exceed 5 seconds. It's considered that because there is a lowered value here, that the longer duration can occur. There has been common myth that maybe because the potential voltages aren't anywhere near this, they're probably nearer 30 volts. They are in the ELV world, and technically they shouldn't require a maximum disconnection time at all. There is argument for that, but it's kind of rubbish because you still need to protect against fire. So you should achieve disconnection within a time frame. We did the ZS's just now, TN systems, and we looked at how much impedance is required to achieve the current, to achieve the time. Now, the difference between that and this, though, is the voltages, and so they've created a ZS table here just for reduced low voltage. So this ZS table, same principle. The amount of current required to achieve the disconnection time, we know that's 5 seconds. So the amount of current required to disconnect a BSCN 60898 type B in 5 seconds, but it's respective to the voltage. In this case, the voltage is 55 or 63.5. And you can see, obviously, that changes the ZS's accordingly. So do pay attention. Again, in your exam, you can have a question asking you the maximum earth for loop impedance. And if it says reduced low voltage, then you know you're here. This is the ZS table for reduced low voltage. And then read it again very carefully. Does it say single phase or 3-phase? Because that will tell you which column to go for. A single phase circuit is the 55 volt column. A 3-phase circuit is a 63.5 volt column. Read it carefully, understand that. So we have to have this separate earth for loop impedance values because we have different voltages and we then require different levels of current, so we have to have different levels of impedance. That's going to close up on ADS as the principal protective measure. It's a lot of information, but we are going to repeat it as we go through because this is the most common protective measure. The whole principle of installing an earth for loop low enough to achieve a current that is high enough to turn it off in the time frame that is quick enough is the most common thing that we chase around and verify. I'm going to mention a lot later on how that can actually snag you, and you should really be verifying a lot more information with your earth for loop impedances. When you do ZS's, you should be doing a lot more with your ZS's than checking them to the table and writing them down on a pad. You should be rechecking a lot of other stuff, which we'll come to as we go through. But closing ADS, let's move on to the next required protective measure, which is going to be a lot more brief, and that is 412, double or reinforced insulation. Now here we have to achieve basic and full protection. So basic protection is by basic insulation, and full protection is provided by a supplementary layer of insulation. Or basic and full protection are provided by a single reinforced layer of insulation. Right, so common way you will identify this is you'll have with equipment, for example, the class 2 symbol. Now, whilst I said earlier on general protective measures are allowed, throughout the home, it does say here, if this protective measure is used as the sole protective measure, where the whole installation is intended, then It must be under effective supervision. So you can't use this in the home or in an office environment as a sole measure. But you can use it for things like your light fittings and stuff like that. As you probably install many light fittings that are class 2. Absolutely fine. You just need to verify that construction class is maintained and that it's suitable for use. Absolutely fine. A couple of things we need to know with this. It gives us the symbol, the class 2 symbol of 412.2.1.1. The equipment shall be of the following types. It then tells us electrical equipment having basic insulation only shall have supplementary insulation applied in the process of erecting it. So if the equipment is just basic only, during the erection process there'll be supplementary insulation applied to it where there's more risk exposed to it. But when we do that, it does illustrate the symbol, which is the earth symbol with the cross to it, telling us that we must not earth this equipment. Another area I've seen this discussed and used is obviously with Amendment 3. We had the metal fuse boards in domestics, and a lot of electricians started to raise the question about TT systems. Because with TT systems, you're supposed to obviously bring your tails to coming in, but you have your RCD, and the question was, well, the RCD would go into the board, but the protection would be after that point. So how is the board protected, or how is the cables coming into the board protecting that? And the main reason they are protecting that is because the meter tails are actually double insulated. So the protective measure of double insulation occurs in every installation at the meter point to your main earthing terminal, for example, or to your isolator in your fuse board, because meter tails are double insulated. As long as we installed them in a method that actually maintains that construction class. If you, for example, go to a meter tail or a service block, and you see that the outside grey has been stripped far back outside of the enclosure to identify the brown and the blue, technically, whilst I can see that that's so that you can identify one from the other, you've removed the double insulation layer, and and now the protective measure is pretty much void. It's a very common thing I would see on an EICI. If I see brown and blue outside of the meter or outside of the fuse board, then that technically needs improvement. If I open a fuse board up, I should expect to see the tails glanded, in a insulating gland, and then the stripping should be sheathed back all the way to the point of the sheathing should be on the cables all the way to the isolator. They should not be stripped far out of that, because you're removing the class 2 protection. Anything else? We'll move on to the next protective measure, I think, and that is 413. Now this is electrical separation. The electrical separation, basic protection is provided by basic insulation of live parts, barriers or enclosures. Full protection is by simple separation of the separated circuit from other circuits. So the isolating transformer is where the fault protection is achieved, and that is isolating the equipment connected to the isolating transformer from the supply side. So it's a separate earthing world in itself. This is a typical generating set that goes to one piece of equipment. Now, if this generating set went to one piece of equipment, then loops to another, and then to another, this is where we'd be supplying more than one item of equipment, and we'd have to have insulated bonding or insulated equipment communicating between the two. This then becomes a tighter area that requires more levels of skill and control, and so would not be applicable as a general protective measure, and we'll see that later on towards the back. If the isolating transformer is just one piece of equipment, such as your shaver, you can plug one thing in, then that's fine. Alright, that's what this complies to. The whole principle being your supply comes in to the transformer, then obviously the windings on the transformer pass across. There's no electrical connection across the transformer. The protective conductor comes in, it terminates, it does not carry across to the secondary. This secondary side does not know of the primary side. The equipment connected to the secondary side has no potential reference to the primary because nothing comes across. It's its own little electrical system. So if you were to handle a piece of equipment plugged into this shaver, it became live in your hand, you would have no potential to any other part around you. if you were to then take another another socket off of the same transformer, and you plug in something into that one, and you have the one plugged into this one, and they both become damaged, then you have potential. So you must have only one item connected to the transformer. But that doesn't mean your bathroom can't have 5 of these in it, because you have 5 separate cases of electrical separation. That's absolutely fine. Electrical separation actually also carries on into SELV, and we have that illustrated here as the last of the general protective measures, SELV and PELV. Now, PELV isn't separation, but SELV is. So it's separated extra low voltage. So the same principle as this, but the windings are fewer, and that results in the voltage stepping down. The voltage stepping down gets us into that safer voltage. And now we're in that area where we're using a voltage that we like, that is safe. And you'll notice when we get to part 7 that these methods of protection, SELV, PELV, most often SELV, are the only ones left that are considered acceptable in zone zeros of baths and zeros of swimming pools, or higher risk areas, due to the confined conductive locations with restricted movement. Because if anything goes wrong, you're then using a voltage that's not really going to harm you. Still though, in those circumstances, they may restrict the voltage further. So whilst we'd say SELV would be 50 volts or less, some scenarios would actually say, oh no, that's going to be 25 volts or less, or 12 volts or less. So there are restrictions on SELV. But SELV itself is electrical separation and extra low voltage. PELV is actually extra low voltage, but it's not separation. So you'll see with SELV the earth stops. With PELV, the earth carries across. So we have equipment connected to an extra low voltage transformer, but the earth has come along with it. Yeah, could be exposed conductive parts, could be some other reason. It's not functional though, because that was PELV. Okay, but for some reason the equipment requires a protective conductor, so we utilise PELV as the protective means there. Regards to what the regulations say, it's again similar. Basic protection to basic installations to 416 and other circuits. Things we do need to realise with regards to SELV and PELV is we must segregate them. So it says there in general, 414.1.1, protection by extra low voltage is a protective measure which consists of either 2 different extra low voltage systems, SELV and PELV. Protection by extra low voltage provided by SELV or PELV will require limitation of voltage in the SELV or PELV system to the upper limit of voltage band 1, that's 50 volts. Voltage band 1 goes up to 50 volts AC, 120 volt ripple free DC. Protective separation will be required of SELV from PELV and from all other circuits other than SELV and PELV circuits, and basic insulation between SELV or PELV circuits and other SELV or PELV systems. And for SELV systems only, basic insulation between SELV systems and earth. So what it's saying is we need to separate SELV and PELV from LV, segregation. We also need to segregate SELV from PELV, because SELV doesn't like earth, PELV does like earth. And then SELV just needs to be separated from earth. And obviously that's common sense with regards to the way we segregate it. Sources for SELV, isolating transformers, current degree, and that's pretty mediocre stuff. Okay, if we then go over to 414.4.5, we've got, if the nominal voltage is to exceed 25 volts AC or 60 volts DC, or if the equipment is immersed, then basic protection shall be provided for SELV and PELV circuits by installation in accordance with 416.1. Barriers are enclosed in accordance with 416.2. Basic protection is generally unnecessary in normal dry conditions for cell circuits that do not exceed these. So what that actually means is bare conductors, which you may see in some lighting displays, etc. Bare conductors is allowed for circuits up to 25 volts. If you go over 25 volts, you require basic insulation on your SELV or PELV system. 415, additional protection. So we talked about the protective measures. The protective measures must achieve basic protection and fault protection. But sometimes, we just need more protection. Let's call that additional protection then. This is where there's a combination of circumstances or external influence that, there's just extra need or extra desire to provide an extra layer of protection. So 415.1.1 tells us the use of RCDs with a rated residual operating current not exceeding 30 mA is recognised in AC systems as additional protection in the event of failure of the provision of for basic protection or provision for full protection, or by carelessness by the users. So, something like the lawnmower lead is the common example. Protective measures are there, but the user has just been careless and drilled and gone over it, or drilling a cable in a wall. The use of RCDs is not recognised as a sole means of protection and does not obviate the need to apply one of the protective measures specified in 411.414. So it's additional protection, not sole protection. So using an RCD alone is not sufficient. We must have ADS with an RCD for most of our wiring systems. The alternative additional protection is supplementary equipotential bonding. Equipotential, again, we're going to use that word a lot. If you ever struggle with that word, just think of equipotential as equal voltage, okay? Keeping things simple. So, supplementary bonding shall be included for all simultaneously accessible exposed conductive parts of fixed equipment and extraneous conductive parts, including where practicable the main metallic reinforcement of constructional reinforcement concrete. The equipotential bonding system shall be connected to the protective conductors of all equipment, including those of socket outlets. So if supplementary bonding detection is required, it will be required between exposed conductive parts and extraneous conductive parts, and exposed conductive parts and exposed conductive parts, and extraneous conductive parts to extraneous conductive parts. Whatever. It depends on if it's needed. The question is it needed? That's the question. And the answer is, in sections like 702, swimming pools, agricultural and horticultural, which is 705, 705, they'll say, supplementary bond in this area, supplementary bond in that area, fine. Other sections like 701, they'll say you may need to bond, you may not need to bond, and understanding when we need to bond is, it can be a challenge. But it's quite simple when you look at this. It tells us the resistance between simultaneously accessible exposed conductive parts and extraneous conductive parts shall fulfill the following. R must be less than or equal to 50 volts over IA. Right. So the question is, let's look at this picture here. I should really have had a better picture, but let's look at this, right? Let's say this piece of current using equipment is my oven in the kitchen. And coming down behind that oven is a gas pipe. So I have an exposed conductive part, which is in arm's reach of an extraneous conductive part, and I'm thinking, do I need to bond there? And I'm not sure. The answer is, the resistance between those two, you measure. Let's say I get 50 ohms, random number. I now need to say, well, that must be less than or equal to 50 volts over IA. So what's IA? Well, IA is the actual current that will actually disconnect this. Now, if this is an oven, let's say this is an oven and a fuse board in the home, it's likely to be on a BSEN 60898 or a 61009. Now, if it's on a 61009 with an RCD, then for an earth fault scenario, it's going to trip in 30 milliamp. So for all intensive purposes, 50 volts over IA of 30 milliamp is 50 over 0.03, which we said back in TT systems gives us 1667. And this is why you'll see a lot of supplementary bonding is no longer really needed, because the thing that can become faulty has 30 milliamp RCD protection at the origin. So the 30 milliamp for that scenario requires 1667. It's very unlikely you'll have 1667 ohms between accessible exposed and extraneous conductive parts. But if there is no RCD, because maybe you're in a shop, maybe, I don't know, maybe for some reason, maybe it's a 40 amp final circuit, I don't know. You have to work out the current. And so you go to the book and you work out the current. So let me just do this. If I go to Appendix 3, let's say it's a 40 amp 60898. And I said I measured 50 ohms. Right, so 40 amp 60898, type B. Appendix 3 tells me 40 amp B. It tells me it requires 200 amp for instantaneous disconnection. Now I have to be careful how much I use that book though, because I need to understand the real full current relative to the earth loop impedance. But for now, let's go with 200. So 200 amp will achieve disconnection. So 50 volts over 200. 50 volts is the touch voltage. Get calculator out. So the resistance must be less than or equal to 50 volts over IA. So 50 over 200, 0.25. Okay, so the resistance between that oven and that gas pipe needs to be less than 0.25 ohms. Because if it's more than 0.25 ohms, with regards to the amount of current that's going to be required to turn that cooker off, the voltage across this gap could climb over 50 volts. Yeah? I have 50 ohms between these two. I need to now supplementary bond them. I'll supplementary bond them to bring them below 0.25. So the question of do you need supplementary bonding is always dictated by how many amps is required to disconnect this equipment within the required time. I can go through a number of examples with supplementary bonding, but it is just Ohm's law with 50 volts. So, we can do more if we need to on that. Do let me know. Moving on, we have 416, which we've mentioned a few times now. This is the basic protection area, and it tells us basic insulation of live parts. Live parts shall be completely covered with insulation material which can only be removed by destruction. For equipment, the insulation shall comply with the relevant standards. So insulation is only insulation if we can only remove it by destruction, such as a stripping tool. If you can just peel it off, it's not really considered as effective insulation. Enclosures. Live parts will be inside enclosures or behind barriers, providing at least a degree of protection of IPXXB or IP2X. Okay, so the outside enclosure will achieve IP2X and IP4X if it's a horizontal sloped surface. Then when you open up a panel, the intermediate barriers may be needed. So if I open up this panel and I'm there to work on an inverter or a transformer for the actual control equipment through to a PLC, I shouldn't be worried about the barriers in front of the isolator or this switchgear. There should be no live parts within, beyond IP2X, finger safe that we use. So intermediate barriers are very important. All right, and you'll get a lot of this in switchgear and control gear. Okay. That's 416. 416.2.4. Where necessary to remove the barrier opening enclosure or remove parts of the enclosures, this will only be done by the use of a Cura tool or after disconnection of the supply or with an intermediate barrier. Oh, it's got cold. 417. Obstacles and placing out of reach. I've got no more slides to be honest, Brett, but we're right at the end. 417 isn't a general protective measure. This protective measure is putting it up there, out of the way. So this is going to be a controlled type of scenario, such as a substation. You may see it in factories though, for like cranes that go overhead. There may be exposed live parts, but they're up there, and there shouldn't be anyone up there while they're in operation. So those are the requirements. But with regards to what placing out of reach actually is, we do have this drawing, figure 417, which tells us the limit of arm's reach. And so if you look at the images, you can see there, the top left kind of shows you that the reaching limit is 2.5 meters. So beyond that can be considered as beyond arm's reach from the standing point beneath. Then to close it, we'll talk about 418, which is protective measures for application only where the installation is controlled or under the supervision of skilled or instructed persons. So these are special scenarios: a non-conducting location, which is obviously an Earth 3 area, Earth 3 bonding, which again is bonding between parts but no connection to Earth. I had actually seen this once before at the McLaren factory. So picture, if you will, you have a workshop or a bench of connected equipment and calibration equipment and stuff, but you need to make sure that equipment does not become exposed to static shock or any discharges of current charged up by the workers. So they have no connection to Earth, so you cannot discharge any energy or and there's lots of capacitors to take energy away. But still, whilst you're working between parts that are within proximity to each other, you need to make sure you don't pass any energy from one to the other. So they were bonded, but they were not earthed. So there was bonding to make that common between them, but the ability to discharge a current down on Earth was absent. And we mentioned electrical separation earlier on. We said that you can't put more than one item of equipment on one isolation transformer in case you created loops between the two bits of equipment. You can do that with generating sets, for example, but it is a special scenario, and that is in 418.3. Okay, and 419 provisions where automatic disconnection according to regulation 411.3.2 is not feasible. So this is saying if 411.3.2 is not feasible, 411.3.2 was the whole purpose of ADS, really, wasn't it? Hang on. Yeah, the 411.3.2 is automatic disconnection in case of a fault. That's where we started talking about the times, the TN or the TT and the 0.4 and the 0.2 seconds or the 5 and the 1 second. Disconnection times, basically. That says if that's not feasible, then we'll have electronic equipment limiting short circuit current. So if there is a fault scenario, there will be electronic equipment that limits it because that we're not able to achieve that high level. Or the required disconnection times cannot be achieved by a protective device. Then 419.2 and 419.3 are applicable. And again, it's talking about electronic converters that will, it says there, voltage greater than 50 volts. Yeah. So it's using converters or this equipment that will take that and then convert it to an exposure of no more than 50 volts. Fairly boring stuff. But that brings me to the end of chapter 41, and that was a lot, and I think that's enough for this video. Going back to the beginning of the video, the fundamental principle is to achieve protection against electric shocks to persons, livestock and property, and this section tells us that we have to achieve basic and fault protection. Basic protection is against a fault-free scenario. Fault protection is against a single fault condition. And then we said what the general protective measures are. Automatic disconnection of supply, class 2 double insulation, electrical separation, and self and PELV. So those all have basic and fault. So if you had an exam and it said which one of the following has fault protection, barriers, obstacles, insulation, and PELV, you know that it's PELV because PELV has basic and fault. Okay, so do think about these protective measures as basic and fault, all right, and understand what basic is and what fault is. With regards to the protective measures themselves, ADS, 411. There's a lot of information in there with the ZSs, etc. Disconnection times. Get an understanding on those. Become familiar with those. We can do some revision exercise on that, and I'll probably provide some sample questions just to kind of practice that, because that kind of thing does need a bit of practice. Just kind of familiarize yourself with it. Is it a distribution circuit? Is it a final circuit? Is it over 30? All that kind of stuff. needs to become a bit more second nature, so that you ain't dawdling around or wasting your time with that. But we'll finish this video on this one, and next video will be protection against thermal effects, which will be a lot, be a lot more shorter. This is quite a large video, so take some time to consume this, to revise this, to take this in, and then I'll see you in the next video, chapter 42, protection against thermal effects. See you later.